Hello everyone, myself Pushpendra Kumar. Today I am presenting the assignment 3 of solid state CML 661. In this assignment, we will learn the some synthesis methods or synthesis techniques for the materials or the solids. So let's start. First method is the shake and bake method. In this method, first we take the two or more solid powders and mix them so that and heat them in a furnace. First we take some solid powders and mix and heat it in the furnace. So between the boundaries the slow diffusion starts. Slow diffusion reactions starts and product form. Generally these reactions slow because the reaction is happening at the powder form, not in the solid or not in the solution or in the vapor phase. Because solids diffuse slowly, very slowly. So these reactions are very slowly because the reactants may be well mixed at the level of the individual particle, because reaction happening here at the atomic scale or in the micrometer or millimeter scale. So the atoms cannot diffuse strongly, so the reactions rate is slow. There are some process involved in this process. So some process various process involved in the solid state reaction or shake and bake method. First one is the nucleation. Means you can see here, these are the different molecules, MgO and AlTO3. They are arranged idealized reaction mixture है. But in actual it is not found such like that, because it is a idealized form, and in the mixture or in the powder form they are not arranged in a regular manner or in the ideal manner. So here, as they comes contact, so as they comes in contact, they start diffusion, and due to the diffusion, the product formation takes place. We can see here that this is the Mg substrate, and this is the aluminum substrate. This is the substrate, and it is on the alumina surface, and this is the magnesium oxide surface. So here, what happens? Mg and Al comes into the contact and form the spinel product that is shown here. So the second step in this reaction is the growth. What happen in growth? Growth is the stage where the stable nucleus becomes larger as more. Means after if the initiation or the nucleation starts, then the molecules growth combinedly and growth and in a large area. So it is a larger ion as more diffuse, and they form the thicker product layer. They form the thicker product layer. Mg ion moves towards the ion. Here we can see that it is the alumina and this is the MgO, magnesium oxide. From here, Mg moves towards the alumina and aluminum towards the magnesium, and they form the boundaries between them. They combine here and form the magnesium alumina. You can see here. So Mg ions moves out of the MgO towards the nucleus, and aluminum ion moves out of the alumina towards the nucleus. And these ions enter the growing spinal structure and they combine to each other and form the crystal structure or spinal structure form करते हैं MgAl2O4 की. So product layer becomes thicker, और ये this layer becomes more and more thicker. So such the spinal crystal growth happens. As the layer grows, the ion must diffuse through the more spinal, so diffusion becomes slower and growth slows down. As the ions motion increases, or more and more ions come here into the interface, this interface becomes thicker and thicker. So the diffusion starts. Diffusion becomes slow, and due to this, the reaction becomes slow and terminate and going moves towards the termination. So third, the reaction involved in this method is, for example, we if we are making the MgAl2O4 spinal structure, then such type of the reactions happens. First, aluminum and Mg and magnesium oxide, these combines and form the First nucleation form the nucleation, and nucleation by nucleation they form the one molecule. And by the at the interface of the Mgal2O4 and Al2O3. Now, if this interface forms, then this interface also act as a provide surface and the reaction happens again. So Mg2 plus and 2Al plus 3 and 4Al2 alumina, and these forms the 3 Mgal2O3, means growth happen, and hence we can see that overall reaction what we happen. So 4 MgO plus 4Al2O3 gives 4Al2O4, and this is the alumina or spinel structure. This is the spinel. So third method, uh, tech, third process involved in this reaction is epitaxy. What is the meaning of the epitaxy? Epitaxy is the arrangement of the atom. It tells about the arrangement of the atoms on the surface. If we are using any surface, and if the atoms arranged in the in the same crystal arrangement of the, if the new growth or new film is formed at the in the same crystal structure as the surface, then it is known as the epitaxy. Means epitaxy is the oriented growth of the new crystal layer on the surface of the another crystal if their atomic arrangement matches. Means if we know, if we let us consider, if it is the surface and these are the crystals in this surface, and if we are forming a crystal or forming a material on this surface, this is the surface, and we are forming a material and we are deposited by the solid state reaction method. Then other if the product layer formed in the same crystal manner as the layer comes at the atom to atom, then this type of the arrangement, only the surface matches with the only the surface of the product match with the surface of the substrate, then this is known as the epitaxy. This is known as epitaxy. But if the entire internal crystal structure of the product formed with the match with the substrate, then it is known as the topotaxy. There are two phenomena. First one is the epitaxy, and second one is the topotaxy. Topotaxy means internal structure of the product matches with the substrate internal structure. But in epitaxy, the only the surface arrangement of the atoms matches with the surface of the substrate layer. मीन्स सबस्ट्रेट लेयर की जो एटम्स हैं ऊपर, अगर उससे हमारा प्रोडक्ट की लेयर मैच हो रही है, उसके अकॉर्डिंग क्रिस्टल मैच फॉर्म हो रहा है, तो देन दिस इज कॉल्ड द एपिटेक्सी. एंड इफ द product forming is in the same manner as in the internal crystal structure of the substrate, then this is known as the topotaxy. So in topotaxy is the solid state reaction in which the product crystal retain part of the internal structure. Here क्या होता है, internal structure and orientation of the crystal structure. Means प्रोडक्ट जो हमारा बना है उसकी जो इंटरनल स्ट्रक्चर है वो सबस्ट्रेट के इंटरनल स्ट्रक्चर से मैच होती है. Some of the structural features of the reactant are preserved in the product. Means mostly या most of the cases some structural feature मैच करते हैं with the reactants. First move, practical considerations and some examples of the solid state reactions. So in the practical consideration, we think about the what is the requirement for the solid state reactions for the best result. So there are some choices or some precautions to get the good yield or good product. So first one is the choice of the starting material. We have to choose a good starting material or the best or the starting material that can be react properly, and then proper mixing. We have to think about the proper mixing and inert container so that other contamination cannot be occur, and a well-designed heating schedule to avoid the unwanted side reactions and ensure complete product formation. Means we have to think about some choices or some precautions like starting material. We have to choose the good starting material, proper starting material, and proper mixing. We have to think about the proper mixing, and we have to use an environment such as a inert environment and well-designed heating schedule. And we have to heat in a well-designed manner to avoid the unwanted side reactions. So this is the practical considerations we have to choose, or we have to think about that. So first example of the solid state reaction method is the LiO4 SiO4. So in this Li4 SiO4 can be prepared by the reaction. This is first we take the lithium carbonate and react with it SiO2. We heat it about 40 or for 24 hours at 800 degrees Celsius, and it form the LiO4 SiO4. This is our desired product, and this is the carbon dioxide gas that leaves during the reaction. But there are some problems in the synthesis of the Li4 SiO4. The first problem is the because it decomposes, Li2CO3 melts and decomposes readily about 720 degrees Celsius. Means if we heat it directly at 720 degrees Celsius, it melts and it get decomposes. And it also reactive towards the most container materials, including the PT and silica glass. Means अगर हम we are using if we are using the container such of made from PT or silica, then it can also be react with that. So what we have to do to avoid these problems? So we have to use the AU container, that is the less reactive metal. Gold is the less reactive metal, and we have to decomposition and pre-reaction of the LiTCO3 at 650 degrees Celsius for a few hours. Means हमें first we heat this Li2CO3 at 650 degrees Celsius for few hours, and then finally we heat it up at 8 to 900 degrees Celsius overnight. So we can see the reaction here. Means first we decompose it and pre-reaction at 650, and then we heat it at 800 to 900 degrees Celsius overnight. So we can avoid the problems by using these precautions. So now let's the second example. The second example is the YBA2 Cu3O72 delta. So why it is known as the YBCO? It is a highly temperature superconductor. It is a high temperature superconductor. Is the critical temperature is about 90 Kelvin. It can be prepared by the solid state reaction. Is the reaction of this, the preparation of this compound is given as here. So why to first we take the yttrium oxide and copper oxide and half O2 and BaCO3 barium carbonate, and heated it at 950 degrees Celsius and 350 degrees Celsius. First we heat it up to 950 degrees Celsius and then 350 degrees Celsius. So it formed the desired product YBA2Cu3O7 plus 4CO2. YBCO form, it's from the YBCO. But there are some problem also, because can no one method can be perfect or proper. So here are some problems. The problems is BaCO3 is very stable, so it does not decompose easily because it's the barium carbonate. It is the stable carbonate of the barium, of the second group barium, that is very stable, so it does not decompose easily. So we have to apply the higher temperature. Even at higher temperature, it retains CO2. If we also heat it at a higher temperature, it also contains a CO2. It cannot completely release the CO2. So this is the second drawback of this molecule. This leftover CO2 interface with this reaction and slows the product formation. And this CO2 do the interface. If it interact with the interface, and it slow down the reaction. So this is also a drawback. Why? Because can react slowly with the atmospheric CO2, and due to this CO2 formation, this YbCO2 react very slowly with this atmospheric CO2, and this is the main cause of the decomposition or the reversal of the reaction. And due to this CO2 formation, the reaction gets reverse. This reaction can become reverse due to this CO2 formation. So we have to choose some another method or some improvement in this method. So And the oxygen content of 7 to Z delta of the YBCO product is variable and must be controlled to optimize TC. So we have to choose some or modifications in this method. So there are some solutions that from by using these solutions we can protect our product from the CO2. So first of all, react in a CO2 free atmosphere. First we have to use an environment such as where is no CO2 and with the BOC3 as a source of the BO3. And and we have to use the BaNO3, barium nitrate instead of the BaCO3. We have required in this, we have to require the BaO source. In the product there is the BaO source, means we have to use the precursor such like which can give the BaO. So we have to use not use the BaCO3 and we have to use the barium nitrate at place of the BaCO3 for the source of the BaO. First is the first modification, we have to use the barium nitrate at place of the BaCO3, barium carbonate. And then second we should have do make the pellets of the reaction mixture after decomposition of BaNO3. Means when this barium nitrate decomposes, we have to make the pellets. We have to make the pellets and react these on a bed of the pre-prepared YBCO. And then this decomposition after the decomposition of BA3, we prepare the YBCO by using this the decomposition by like a bed. After the reaction at 950 degrees Celsius, carry out final heating at 350 degrees Celsius so that O2 release to achieve the desired stoichiometry. First, we break the BaNO3 at 950 degrees Celsius and then again we heat at 350 degrees Celsius so that O2 can release and we can get the desired product, that is the YBCO, YBS2CO3O7. Now let's move. This is the second method, combustion synthesis. This is the combustion synthesis and the solid state reaction method. So in the combustion synthesis is a method where the reactants are mixed and then ignited so that the reaction released a large amount of heat by itself. Means the name is the combustion. Means we have to produce the means we here the reactant molecules will be ignited or produce a large amount of heat, and due to this release of the heat the reaction happen itself. So this heat is so strong that it makes the reaction complete within the seconds or the minutes. Means as unlike the normal solid state reactions that take hours. Means as we have seen that in the solid state reactions are very slow because there is the interaction between the powder form or the micro level or the millimeter level. But here, when we mixed the reactants, a large amount of it, we take the reactants such like which are highly exothermic, which can produce highly exothermic reaction. So we take such reactants that release high amount of the heat after the reaction, and due to this heat produced, the reaction happens further. So combustion synthesis mainly include two important approaches. There are two types of the process involved in the combustion method. First one is the self-propagating high temperature synthesis. Means we choose the reactants that produce the large amount of heat, and due to this large amount of heat, the reaction happens itself by own self. So it is known as the self-propagating high temperature synthesis. It means HSHS. So let's see what is this. SHS technique was pioneered by the Mahjanov and co-workers in the Russia. This is the scientist name that first synthesized by this method. So Marj Marjanov and their co-workers in Russia. In this synthesis, the starting material react highly exothermically and creating the extremely high temperature in seconds. Once started, produces its own heat and continuously automatically. Means first we choose 10 reactants so that they can react in a very high exothermically manner, and they produce a large amount of heat or temperature in seconds or minutes. So the reaction So if once a reaction start, then it continues automatically and the final product happens. So the starting material may be classified. So there the starting material are known as the two types, fuels or oxidants. First act as a fuel and other will act as a oxidants. So we can see the example, the thermite reaction. In the thermite reaction, here aluminum is acting as a fuel and Fe2O3 oxidant. It is acting as a oxidant. These two combines and release the enough heat. They produce approx 3000 degrees Celsius temperature. That is very high, a huge amount of the temperature. So due to this high temperature, the reaction happens very rapidly. So this is the self-propagating high temperature synthesis. This means we choose some such reactants so that they react very highly exothermically, so the temperature of the container increase very highly and rapidly, and due to this temperature difference the reaction happens continuously and form the product. So this is the SHS, self-propagating high temperature synthesis. The other method is the of this solid state method. This is the solid state metathesis, SSM. In this method, we take the in the synthesis the reactants react and form the such product so that solid state metathesis, so that one of the product, usually side product, as has a very high lattice energy and its formation provides the driving force for the reaction. Means is in this method we take some such reactants that form any side product and plus side product, and this side product have very high lattice energy, and due to this high lattice energy, this reaction favors the product formation. This reaction goes in the forward direction. So such like the reactions is known as the solid state metathesis, SSM. So here is an example that can be prepared. This is the 5Li3N and TaCl5. This is giving the sodium nitride and LiCl4. We know that LiCl4 is have very high lattice energy. It have very high lattice energy. So due to this high lattice energy, this reaction happens and goes in the forward direction to form the sodium tantalum nitride. Tantalum nitride. So LiCl side product is the side product. Our desired product is the tantalum nitride. It forms and evaporates the or melt and helping the reaction to complete. So due to this lattice energy, this high lattice energy, this reaction happens and forming the tantalum nitride. That is our desired product. So let's move further. The other method of the solid states, yeah, so materials is the mechanosynthesis. Mechanosynthesis, or we can also known as mechanical method. This we can is called also as the mechanical method. Mechanical method of the synthesis of the solid state reactions or materials. So in this mechanosynthesis, we take the material in a box, like it is like a it is also known as ball milling method. It is also known as ball milling method, in which we take the our sample in such a container where some small bowls, milling bowls are present, and we put the sample in this like container and we rotate this container very high speed. And due to the rotation, and these ball milling also rotates with the our substrate or our material, and due to the collision between the bowls, milling bowls, our material gets decomposes and convert into the nanoparticles, and it convert into the nanoparticles. So what we have to do in the mechanosynthesis? Mechanosynthesis is a powerful, energy efficient method for making the nanoparticles by mechanical grinding. Here happens the grinding of the our substrate. We take the substrate in the container, and due to the rotation and mechanical rotation by the balls, the powder breaks and convert into the nanoparticle. It is the cheap, fast and capable of producing the new or non-equilibrium materials. It is very cheap because we have not required any high temperature or any other things. We have to require a container, and we have to rotate this container. So there is very less amount of less amount of this is the cheapest form, cheapest method to synthesize the materials, nanomaterials. So we can prepare the Zn2SNO4 by this method. Recent nanosite, this is the recent nanosized grains that is synthesized by mechanochemistry. So let's see other methods. First one is the second big method. We say see other methods in the second big. This is the second type of the methods to prepare the solid states or solids or materials. So second one is the low temperature or chemi-reduce method. So chemi-reduce method, what is happening here? In chemi-reduce method, it is soft chemistry methods. Reaction done at low temperature in gas, liquid or solid phases. These methods allows the reactants to mix atom by atom, giving much better control over the composition. Means in the solid state method or second bake method, we are using the powders. Instead of the, we are using the powders or we are taking the reaction between the solids or powder form of the reactants. But in the chemi-reduce method or low temperature method, we use the substrate or initial substrate or initial reactants in the liquid state or in the vapor phase or in the gas phase or soft solid phases, so that we have to require very less temperature to react with them, because here the reaction happens at the atomic level or atomic scale. But in the solid state method, the reaction was happening at the micro level or the millimeter level. So here the temperature or energy or the energy use will be very less. So first method in this low temperature method is the alkoxide sol gel method. Sol gel synthesis, it is also known as the sol gel synthesis. So in this method, first we choose the alkoxide of the particular method that we have to prepare. So the alkoxide method is a low temperature solution based technique used to make the oxides. First, what we have to make is from this, we can make oxides, mixed oxides, materials with the excellent chemical homogeneity. And in this method, first we have to choose the metal precursor, or that is the alkoxide. First we take the metal precursor, that is the metal oxide. That is if we have to synthesize the silicon oxide, so we have to choose the tetraethoxysilane SiOCS3 CS2 or CS3 का whole form. This is we also know as the TEOS. If we have to prepare the titanium, then we have to use the TiOIPR ka whole form. And if we have to prepare the aluminium oxide, then we have to use the aluminum bauxite. First we choose the metal alkoxide and then we add the water and get the hydrolysis or condensation. We can see here if we are using the what happening in the here. So let's see how the reaction happens. Means if it there is the Si and this is the OCS2, CS3, CS2 and CS3, and here also four things, four molecules are also acting, and we take the water as a for the hydrolysis. We can see that water has the H plus and OH minus. It has H plus and OH minus. So here the both can act as a attackers. Here H plus can also attack, or here OH minus can also attack. But in generally, I am saying that generally we can see here is the bond, and if we break this bond, here we can add the H and OH here. So here we get such like things SiOH, OH and OH. Now this molecule, this is from the hydrolyzed product. Now this molecule or this compound that is formed react with the other such other molecule that is after the that form after the hydrolysis. Now these two remove the water molecule from here and they combine. Here from here minus water molecule is released, 2 what 2H2O is releasing, and they form such like product I am writing here SiO, OH and OH, OH and OH. Similarly, first next molecule comes here and form the oxygen. This hydrogen can will be released, and this from the silicon SiO bond. Thus, this molecule's growth increases rapidly and form a polymer or polymer-like molecules. So first we take the hydrolysis as I seen here, as I saw here. This is the reaction happening. It is here we take only one more. Here a plus molecule is plus is left, so it is a typing mistake. Plus is left. So we take the metal alkoxide, then hydrolyze this, and this form the SiOH couple, and this is the side product. Here we can say as it HOH here attack, so CH3 CH2 OH is released, and this is the side product, act as a side product. So second step is the condensation or polymerization that I have shown or explained earlier. First, these two form by the hydrolysis. Now these combines to each other and form a gel-like or polymer-like structure. This is the other molecule, SiOSi. Here, from here, water molecule release, and they form the, this is the gelation. They form the gel. And from the gel formation, we can form other things by different processes. If we precipitate, then we get the fine uniform powder. If we spinning this, then we get fibers. And if we coat this on a metal, on any other film, then it's from the dense film or zero gel film. And if we create the gel and after evaporate this gel, then this is form the zero gel. And if we go at the centering, this can form the sphere or the nanorods. And this, if we drying, supercritical drying, then it is from the aerosol. So different things can be prepared, or different things can be generated from here, from this reaction. So this is the plus point for this reaction or for this method. So now we can see that what are the factors affecting the alkoxide sol gel method. So the properties of the sol gel mixture, its decomposition, structure, and thickness depend strongly on how much hydrolysis and condensation happen, because we are taking only two steps here. First one is the hydrolysis and second one is the condensation. So according to this, how much the hydrolysis is happening or how much the condensation is happening, on the basis of these two factors, the product will be affected. So there are two types of the hydrolysis methods. Hydrolysis can be two types, and also first we choose the metal oxide, making metal oxide from the different. If here in the earlier example, we take only the same metal or same non-metal, that was the silicon. But if we use the different metals, M or M star, M or M dash, if we starting precursor are the different metals of the different metals, then we can get the polymer or the soul of the different metals that include the oxygen and this like form. Here, from here, water molecule is released and they form the MOM bond. So this is the first method, making the oxides. First make the oxides of the different metals. Second one is the hydrolysis also affect the product, and hydrolysis are the two types. Here hydrolysis can be the two types. As I earlier said that here H plus can also attack, or OH minus also attack, because there are both present in the water. So in the base catalyzed hydrolysis, first nucleophilic attack of the OH minus takes place. Here, if I can show here, there are the SiOR, this is the alkoxide, metal alkoxide, silicon alkoxide, OR, OR. If I attack the OH minus, then OH minus attack this and this will be released. And the present H plus will react with the OR and this from the Si, OH and OH, and OH. Also, all the OH will be OR will be replaced with the OH, and there also from the other ROH. So here, and again here only one OH is attacking, but I have shown all four OH if all the RO molecules is replaced with the OH, and we get the RO, or there is the present in the H plus, so H plus can be attack or mixed joined with the RO minus. So this is the first method when the hydrolysis can occur, and the other method for the acid catalyzed hydrolysis or H plus can attack on the silicon. So if as H plus attack on this, then it form the SiOR3 and RCl. So they also affect the product formation of the by the Sol-Gel method. First here क्या होता है, here proton activates the alkoxide and make the OR easier to leave. So this was the synthesis of the Sol-Gel by the Sol-Gel method. Yeah, here it is the example, first example that can be prepared by the Sol-Gel. So we are preparing here for the MgAl2O4. So first we take the appropriate reagent. We have to choose here magnesium alkoxide methoxide, magnesium methoxide, and other second we have taken the aluminum tertiary butoxide. We mix them and hydrolyze condensation and drying, an amorphous gel is obtained. If we condense these things, they can form, here we can see what they can form. Here will be the Mg and here will be the aluminum, and there they combine with the oxygen, and here will be the OTBU, and here also will be the OTBU, and here will be the OCS3, and here OCS3. Means there was, firstly we have take these two things, and if water molecule attack on that, then they form the these things. I am writing here Mg, OH, and OH, and OCS3, and OCS3, and this other thing will form the aluminum TBU, and here OH and OH. After the attacking of the, or after the hydrolysis, these two forms the these things, and after the condensation they form these things. So we can prepare the magnesium aluminum aluminate MgAl2O4. So let's move further. Synthesis of indium tin oxide. So we can prepare the indium tin oxide. What is the firstly we have to know the what is the indium tin oxide. So ITO is an transparent conductor that can be used. It is used as an electrodes in the energy efficient windows, means smart windows. We coat the material on the on the ITO film, and due to the chemical reaction, this material electrochromic material changes color, and it in the color state the window cuts the IR radiation, so heating cannot be occur. Made by the soldiers uses in the tin oxide alkoxide. First we take the indium alkoxide IOR and tin oxide tin OR, and by mixing these two we can take here 3 and also here 4 SN OR ka whole 4. By mixing these two forms they form the Sol gel. First we form the sol and then gel, and a thin film is poured onto the substrate. On the substrate is dropped into the liquid. Means as we have seen earlier here in this diagram, first we form the sol or gel, and then if we coat on this thin film, it is the metal film or any other film that where we have to deposit the this gel thing, this film, ITO film. So this is the glass plate. Generally we use the glass plate to deposit the ITO film. So first we make the sol or gel of the ITO, and then we coat it on the glass plate, and on coating the glass plate we get the dense ITO film, or that is the conductor, and electrode. It can be used as a electrode. So this is the method to prepare the tin oxide, indium tin oxide. So other coating we can also be Other than the ITO, we can also make other coatings. This is the TaO25 we can use for the precursor. For this, we have to use the TaOCS through CS3 ka whole 5 on the silicon. That is the insulating capacitor. And for SiO TiO2, we use the silicon wafer. And that is the anti-reflective solar cell and coatings. So these are the other coatings that we can do by using this method or sol gel method. Now moves further. The third method is the sol-gel method. Sol-gel methods using the hydroxide and the colloidal chemistry. So in this method, what we do, in this method, it is a low temperature chemical method. That is the low temperature chemical method, and in which metal ion in the solution form polymeric hydroxide species by adjusting the pH. Means first we take the metal precursor and we put it into a solution which form the polymeric hydroxide species, and by changing the pH its property changes. These salts gradually link together to form a gel, and which can be dried and heated to obtain the uniform oxides. Often used as a coating, we can use it as a coating also, as we have seen in the last, uh, later diagram. We can also form the fibers or ceramic shapes. So it is the synthetic route of the preparation of the any material by using the hydroxide, sol gel using as a hydroxide. So first we take the metal oxide precursor and we add the water, hydrolyze these things. First, we take the metal precursor, aluminum oxide, and we hydrolyze this. And after hydrolyzing, it form the aluminum hydrate, and we change the pH. We change the pH, and due to the changing the pH, it forms the LiH2 whole 5 and OH2, and it can also form these things. If we again change the pH and attack the OH minus, then this form the gelation, and attack and it forms these things. And if we heat again, it can also be generate the initial precursor. So we can prepare the hydroxide or sol gel method by using the hydroxide. So let's move further. Synthesis of the zeolite. How we can prepare the zeolite by this method? So we can see here. First we mix the sodium aluminate. First, we mix the sodium aluminate and sodium silicate in the water. First, we take the both precursors and mix in them in the water. Now add the NaOH to adjust the pH. We add the NaOH, so NaOH OH minus of the NaOH attack at these things and adjust the pH. The mixture becomes a gel, and due to this OH minus or due to this changing of the pH, this mixture becomes in a gel. Gel form कर लेता है at room temperature. So we have required very less temperature here, which is a thick jelly-like material containing the aluminum and silicon. So if we get the gel have the aluminum and silicon also. Now we heat the gel in a sealed container and water with the water autoclave. Means there is a container of the to synthesize this type of the material, that is known as the autoclave. We have pasted an image we will see in later in this video. So sealed in a container water, that is known as the autoclave. This controlled heating helps aluminum and silicon atoms arrange themselves into a crystal framework, and a microporous structure called the zeolite is produced. Zeolite have the channels useful for the ion exchange, trapping molecules and catalyst. So it used as a separation. It can be used for the separation of the different solutes, solvent or solutes. Zeolite also used for the solute or solvent. Means first we take the sodium aluminate and sodium silicate and add the NaOH. And NaOH change the pH of the mixture, and due to changing the pH of the mixture, these form the gel. And when it form the gel, we heat this gel in a we autoclave this, and after autoclaving we get the zeolite. So this is the reaction that is used here in this synthesis. NaAlOH ka whole 4 react with the NaSiO7, Si3O7, Na2SiO3, Si3O7, and they form the gel. First they form the gel, then we take this in hydrothermal conditions. Means We take an autoclave box or autoclave container. This is like that. Here, this is a completely closed. We tight it with the bolt, with the help of the bolt, and it put it into the oven to heat. And means we do the hydrothermal conditions. We apply the hydrothermal conditions, and after applying the hydrothermal conditions, it form the zeolite. That is these things. So let's move further. Hydrothermal and sormothermal synthesis. The next synthesis, first we have seen the solid state reaction, second we have seen the Camet-Dew's methods, and third is the hydrothermal and sorvothermal synthesis. So, there is the difference. There is no difference between the hydrothermal and the solvothermal synthesis. There is only difference of the solvent that we are using here. Solvent, there is a difference in only solvent. In hydrothermal, we used the water molecules or water as a solvent, and in solvothermal we used any other solvent except water. So if we are using water as a solvent, then it is known as the hydrothermal, and if we are using the any other solvent as a solvent, then it is known as the solvothermal. So hydrothermal, we take in this synthesis, the reactants are heated in a water or steam at a high pressure and temperature. This is the autoclave box that we are talking about that in the last slide. This is like these things. It is the Teflon box where we put our solution, and this Teflon box is put it inside this chamber, this inside this autoclave chamber. This is the autoclave chamber, and put the solution. Reactants and water are placed inside a PTFE linked cylinder that is known as the Teflon. It is the Teflon, polytetrafluoroethylene. It is known as the Teflon. Polytetrafluoroethylene is called as the Teflon. It is the Teflon cylinder. Means first we take the precursor solution and mix them. After mixing, we put this solution into this Teflon box, and this Teflon box is put it into this autoclave chamber, and this autoclave chamber is put it on the oven to heat. This oven, it is put it in the oven to heat, or a Teflon cylinder or bomb. It is also known as the bomb. This things also known as the bomb, which is either sealed or connected to external pressure control, and oven is controlled by the vacuum pump or the external pressure control system. This bomb is placed in an oven usually at a temperature range of the 100 to 150, 500 degrees Celsius, and pressure is controlled either externally or by the degree of falling in the sealed bomb. So we control the pressure inside this by, we cannot control the temperature, we cannot see or we cannot measure the temperature inside this autoclave box. So we control the temperature of the outside of the outside environment of this. So you take it in the oven where we can control the pressure. So this is the pressure versus temperature curve that affect due to the presence of the volume present inside the Teflon box. So this is the Teflon box, and this is the outer autoclave box. This is the pressure and temperature relation. If we use the small volume of the precursor solutions, then the PT curve will be such like that, these things. And if we increase the volume, the PT curve changes its position and it goes towards the Y direction. We can see here, it is the 90% of the volume of the Teflon. It is the Teflon box, and it is the volume percentage with respect to the Teflon box. If we are using 90% of the solution with respect to the Teflon volume, then the PT curve will be like this. And if we are taking 80%, then like this, 70% like this, and at 60% it like this. So it is the temperature pressure curve at the different volume percentage. So, and this is the diagram of the Teflon box and the autoclave box. So let's move further. As I already say that hydrothermal and solvothermal are the same things, but there is only the difference between the solvent we are using. In hydrothermal, we use only the water molecule or water DI water as a solvent, and in solvothermal we use the other solvent. We can use the other solvent. So we can see here solvothermal synthesis is similar to the hydrothermal synthesis, but uses supercritical solvents or solvent mixture. But here we use the other solvents. We can use as a PEA, yeah, or IPA, or hexane, or PC, propylene carbonate, such like the solvents we can use in this solvothermal synthesis. For example, here we can see for the Li2MnSiO4 of the current interest as the lithium battery cathode. It is using as a lithium battery cathode, and it is synthesized by the phase pure at 300 degrees Celsius and 38 millipascal in 5 minutes in the supercritical water ethanol mixture. Here we use the solvent as a water and ethanol mixture. So we can use also the alcohols as a solvent in the solvothermal synthesis. This is the same diagram. First, in this we take the precursor solutions and mix them very well, and after mixing we put it into the Teflon box, and after putting this Teflon box is put it into the autoclave box, and this autoclave box is put it into the oven, micro vacuum oven, and after getting from the oven the crystals form or the compound forms happen. So now let's move further. So this is here also the same graph. If we increase the percentage of the volume, the curve, PT curve shifts towards the Y direction or Y axis. So here we can say at 10%, this is the graph. At 20, this is slightly moving towards the Y direction. And if we reach at the 90, the graphs becomes very sharp. So this is the pressure temperature relation for water. It is for the water and alcohol. Sorry, it is the typing mistake. It is the water and alcohol. And this is the hydrothermal bomb representation. So thank you. That's all for the assignments. Thank you.